our main focus is going to be on the linked list data structure. So the linked list structure, again, in the back, it's a collection of data, but it's a little bit different from what we're basically doing in ArrayList. So who remember what is a linked list? Everybody should.
Linked list is a list of variables.
What is the difference between a linked list and array list? What are the most important characteristics of a linked list? Go ahead. So first of all, we don't have pointers in Java, right? So, but yeah, we're basically going to have some sort of data structure that link to each other. So do you want to add something to it? So what is that data structure that we point them or basically link them to each other? What that is called? Node, right? So you kind of now refreshing your memory, because I'm sure you guys, most of you are familiar. So basically in the linked list, the idea is that we're going to create this node. I'm going to show you a node as a box. We're going to create these nodes, and each node is going to have the elements in it that we're going to store, right? So it's going to store the element. And it's also going to have a very basic one. We can implement multiple different kind of linked lists, but in a very basic one, is going to have a link, as your friend says, to the next node. So we're going to have a chain of these nodes. We're creating nodes, which is an object, basically, object node. And then in each node, we have an element, and also we're going to have a reference, storing a reference to the next node. Okay, so basically, if I have two nodes in my list, my first node now needs to know who is next. Do I have anything that I can draw? Okay. So we're storing the elements in the node 1. Example A is going to store in our very first node. And then the second node, we're storing B in it. And the first node now is going to point to the next one. So since each node itself is a separate object, they're going to have a separate place in the memory. So basically, if I'm looking at, and I'm just trying to compare them, so here, if it's my, again, my memory, if my node 1 is here, and I store A in it, my node B maybe is a completely different place in the memory. But how I'm going to find it, since I have the addresses stored in A, so if I have access to A, then from A, I can go to B. And if I add another link, another node to this list, right, and I start, I storing, for example, C in it, then I have to tell B immediately that where is the location of C in the memory, right? So then imagine it's here, then B is going to point me or help me to find that in the memory. If I, as also you remember, if you have an object in the memory or a place in it and nobody pointing to it, nobody referring to it, what is going to happen to it in Java? Garbage collector is going to collect it. So if you forget, your data structure is not maintaining these new nodes that you're adding to your linked list, then you're going to lose them, right? So you're going to make sure immediately when you're creating or adding a new objects in the memory, you're getting the address of it and you're giving it to the one of these nodes to maintaining it. So if you're looking at this linked list that I have, the A, B, C, everybody can see it, by the way, right? Because I don't have the student view, so you can see A, B, C somehow. Okay. So if you look at this, I don't have any problem probably finding B or C if I have access to A, right? But do we have access to A right here? Who is storing A? So you see that we basically completely lost this linked list that we created. So we need a data structure to kind of own this chain of nodes that we're going to create. And by owning it, it's basically going to tell me who is the very first one at least. So if I have the very first one, then I can easily find the basically other element in the list. But I have to do it one by one because I don't have access. You know, they're not back to back in the memory. So immediately, if I want really look, I'm looking for C, the only way I can go to the C is, you know, through A, right? So I have to go to the very first node. From first node, then I have to traverse the nodes one by one to get to the basically the last one that I'm looking for it. So this is exactly opposite of what we had in the array list. Remember, if I want to go to any element in my array list, I can just use the index of it and I directly go there. So it's order of 1 for me to have access to my element in the array list. But as you can see here, that's not the case. I have to traverse the entire array one by one in order to find it. So, or access to that particular node. So what does that mean? If I have n elements in my list, my linked list, and I'm looking for the very last one, so let me increase this. Like imagine we have, you know, more nodes coming up, and then I have to be able to somehow create some dots here. And then some later on, I have another one. So, and this has become my very last node, for example. And this is the node number n. So, and it happened that I'm actually looking for that, right? So I have this element here, like E, and I like to have access to that. So I have to go all the way to that because there's no other way, right? So I have to start from the very first one, and I have to go all the way, traverse them one by one, finding n-1 different address until we get to that particular location in the memory. So that means if I want to access to element in my linked list, how much time I have to spend, or what is the complexity of it? Order of n, right? So it's like a linear search. Remember last time we talked about linear search? It's almost like that, right? So if you're lucky and you're looking for the element in the beginning, then you know, it's maybe very fast. But we're always, then we're talking about the big O notation, we always talk about worst case scenarios as well, right? So worst case scenario for us in the linear search was that the, you know, either it's not even in the list or it's the very last in the list. So it's also similar to that, right? So if you want to go to your linked list, since you have to traverse the entire linked list to get to the element in the end of the list, that means you're going to have access you know, to element in the order of n. So now the question here is gonna, you know, some of you may ask me, okay, so then what is the point of using linked list if it's going to take us even longer to store the element in it? What do you guys think? Is it? We already talked about the problem with ArrayList that can create memory problem for us, right? Because of the fact that you may store larger capacity and then you never use it. So what else? That's not probably the case. What else? Yes. You can keep what? So I don't know if everybody can hear you. So you're suggesting that we can add more data to our linked list without what? Without basically allocating memory from the ahead of time, right? So yeah, that's true. So basically you can add elements into your linked list very faster. It's really going to take us actually order of 1 to add element, right? Whenever we find the location of it and we start adding, when we want to add it to it, it's going to really take us order of 1 to add it. And I want to give you the comparison, right? So imagine I call this is my first element, and I haven't talked about who's going to hold this first one, right? Somehow somebody has to take care of it. But we will also for sure know that we have to have the very first one stored somewhere. Otherwise, we're going to completely lose the entire linked list. So imagine now I'm going to create a new array, but this time a new node. Sorry, and this time I want to add it to my linked list. I'm going to add it to the beginning of my list. So I have a first and end, maybe. Right? So you can have maybe that as well. So If I want to add it to the beginning of my list, right, the only thing I have really to do is create the array, the new ones. I'm going to call it, I don't know, B, another C, okay, C1, for example. So I have to create this node, and I have to tell this node who is your next. Since I'm trying to add it to the beginning of my list, right? So who's going to be the next to this? The first, right? So basically now I only have to tell the first that instead of storing the address of A, now you have to store the address of this C1 that I just created. So you're just changing the address. So after you create a node, you have to just change the address. Changing the address and copying one address on the top of the other address is order of 1, right? So basically that fast, you can add element to the beginning of your linked list. That easy. Order of 1. I just did it, right? Just added a new node. This is my new node, right? And then I just changed the reference of my very first node to this one. So this become my new. Now do the same thing on the array list that we had on the top. Imagine also I have an array list of size n, and now I'm trying to add a new element in the beginning of my array, basically at index 0. Can I do that? And imagine we have enough capacity, or it's going to be handled. Can I do that? Can I add element to the beginning or basically index 0 of my array list? Yes, we can. But what we have to do? You have to shift everything, right? You have to basically make a space for it, right? Because you don't want to copy it on the top of the index 0, right? You want to keep that, but you want to shift all of your elements. So you can insert this new element in the beginning of your array list. So that means if I want to add it to index 0, then I have to copy all of them one by one to the next address. So I have to shift them. So if I have n elements in my list, then how many shifts I have to do? N. So n element in the list, right, already, and I want to add another element to the 0 position. I need to shift all of them. How many of them I have to shift? N minus 1 of them. So that means it's going to give me order of n to insert element into the array list, right? So accessing element was order of 1 in any index, but inserting or adding element to the array list is going to be expensive, right? Because you have to do it in order of n. So basically add elements now, as you can see, is going to be in the array list is going to be order of n. But we did it right now in our linked list immediately, order of 1, right? So that's the difference. So we're going to talk about the remove. We're going to be the same scenario happen. If now I'm going to remove the very first node from my linked list, I only have to change the address. Order of 1 again, right? Just copy an address on the top of the other address, and the new node, that node is going to be garbage collected, but now referencing to it, right? We're going to lose it. The opposite of what we just did for adding it. But if I want to remove an element at index 0, which is worst case scenario, again, we're always then talking about complexity or big O notation. We're talking about the worst case scenarios. So if I want to now even remove elements from my array list at index 0, imagine, it's also going to take me order of n, right? Similar to what we have, because now I have to do opposite. I have to shift everything. At that time, I shift everything to the right. Now I have to shift everything to the left, right? So I can basically get rid of the very first element in my list. So adding and removing elements from your array list is going to take you order of n, but accessing elements to your array list is going to be very fast, order of 1. In the opposite, in the linked list scenario, accessing elements is going to take us order of n in the worst case, but adding and remove is very fast. It's order of 1. Immediately you can add in, remove the elements. So that's exactly the difference between two. That's why we have these two data structures. So you have to always, whenever you have your any application, you always have to do this to kind of do your brainstorming and analysis and try to see exactly what you're trying to do in this particular application that you create, and what is you're going to store, what kind of data you have to store, and how are you going to use this data. So if you have a data, many times we have a specific size of data, and we're only going to keep accessing them. We're storing them, and now we want to keep accessing them to use those data. Basically, we're using it as a storage, and we're going to keep accessing them and retrieving, and so basically, randomly be able to use them. So definitely ArrayList is going to be a very good candidate in this scenario, right? Because we're not going to remove too many elements. We're going to create this ArrayList first one time, and then we're just going to have access to any of these elements as much as we want. So accessing to any of those elements is order of one for us. So it's going to be really very efficient. But if I have data that it's going to keep changing, and I'm going to keep adding and removing elements from my data, so this size of the length, the collection that I have is going to keep changing. We don't really know how many elements we have, and then we're going to maybe start adding and removing elements from it. So it's going to keep changing. Basically, we have this kind of like a target, moving target. Then definitely, ArrayList is not a good option. First of all, the access to these elements can take the order of n. That's one problem. Another problem is depends on how many data you're trying to remove and add. You may waste a lot of memory, or you have to keep calling this resize method. And imagine when I resizing, what's happening? We basically have to copy everything from a block of memory, create a double size array, and then move everything to that new block. This is expensive too, especially if you have an element already in your list. Creating a new block of memory and copying n elements from the old one to the new one, that also order of n. So they're adding a lot of complexity. And now imagine you keep trying to add new ones and remove ones. So you're wasting a lot of memory and overhead of resizing. Yes?
If there's a Java automatically cleans the code, the excess memory that's not being used.
But not when you allocate it inside your array list. You can it's not going to go inside your array list element. Remove the elements you already allocated, and that's one reference to all of them. So you cannot do that unless you go directly call this trim to size whenever you feel like you have to do it. And that's also expensive again. So you have to again cut back, and that means you have to go back and create a new array and copy everything back. So that's an overhead, extra overhead that we have. So that's why I ask the students, if if like you have elements and you already know the size and everything, you don't really need to use ArrayList. Just use the fixed size array that Java provided, because in the background in the ArrayList object also you have array anyway, right? So, but again, back to the question, this resizing have a lot of overhead, right? So when you have a lot of resize, and your elements keep going to change, so you're going to keep adding and removing elements, the ArrayList is not a good option. So the best option in those scenarios is going to be the linked list. And the same thing for linked list, right? So if you have a lot of access, you're looking to access your elements in your linked list, then the linked list is not a good option, because just having random access to an element is going to take your order of n in worst case scenarios, so which is not going to be a useful data structure in those scenarios. So that's beginning. So each of the data structure have their own advantages and disadvantages, and so whenever we're trying to do something, we have to think about exactly what types of data we have and what we really want to do with this data, and then so we're going to pick a correct data structure based on that. So any question about the